Chapter 5 actually has 5.1 through 5.6. 5.1, 2, and 5 are kind of shortish. 3 and 4 are fairly involved. Okay. They're kind of tough. 5.3 and 5.4 are kind of tough. 5.6 actually, we will do a separate worksheet for 5.6, and that'll take 2 lectures. We'll do actually 2 lectures on that because it's really, the book is a little weak on what it has. So we'll actually do a separate thing there. So what that amounts to is that we have 6, 7, and 8, chapters 6, 7, and 8 left. And we have to finish this between February, March, and April. So we'll be running right up to it. So just be aware of that, okay? So we're gonna be a little tight here. Okay, so that means let's go ahead and get started. 5.1, extreme values of functions. Extreme values of functions, let's go to page 193. We're on page 193. Okay, as we know, there are absolute extreme values and then there are local extreme values. Okay, so let's talk about the absolute extreme values first. Absolute extreme values first. Let's go and look at the green box. In the middle of page 193, there's a definition of absolute extreme values. Let f be a function with a domain D, then f of c is the absolute max on D, if and only if f of x is less than or equal to f of c for all x in D. Makes sense. Right, and absolute min on D if only if and only if that. Okay, well that makes sense, right? So also, we also call the absolute extreme, we also call that the global max and global min. And we've used these nomenclature before. We've used them before, right? It's not the first time we're talking about absolute max or absolute min, okay? Now let's go look at example number 1. Negative pi over 2 to pi over 2, f of x cosine x takes the maximum value of 1, so we're looking at the cosine value here. The cosine for it looks like this. Negative pi over 2, so this is f of x is equal to cosine x here, right? So the absolute max would be here, right? Obviously, because this is the highest value, okay? And we have the absolute min here that comes here twice between there and there, right? And that's what they're saying, okay? Okay, so that's that. And then sine x, for sine x, the value goes from here up to here, right? So our absolute max here for sine would be 1 at pi over 2. And absolute min would be negative 1 here at negative pi over 2. Okay, all right. So that's just giving you a overview of what absolute max and absolute min is. Okay, nothing really glaring there. Flip the page, go to example number 2, exploring absolute extrema. The absolute extrema of the following functions and their domain can be seen in figure 5.2. Okay, so if you have y is equal to x squared, so example number 2, y is equal to x squared goes like this, right? So if the domain is between negative infinity and infinity, right, then there is no absolute max because it goes all the way up, right, to infinity, right? And then the absolute min would be down here, would be 0, right? Okay. If we truncate the domain, if we say the domain is between 0 and 2, if we have a domain of 0 and 2, right? Then we don't have this part anymore, and we go from 0 to 2, right? And the absolute max is going to be at this point right here. It's going to be at the end point, right? And it's going to be 4, because y is equal to x squared here, right? So the absolute max would be 4. The absolute min would still be 0, okay? And then if we further go ahead and go like this, okay, now this becomes an open dot, right? This is still, oh, we don't have this part over here anymore, okay? Okay, so what is the absolute max stays the same. The absolute min is what? Absolute min here is there is no absolute min, right? Because you never quite get there, right? You're trying to get there, but it never really gets there because it's not included in the domain, so there is no absolute min, okay? Same way, if I go like this, and I take this guy out, then I'm going to have an open dot here, and I have a closed dot here. Now I have an absolute min here, but no absolute max. Okay? And also if I go like this, where I have both are open, now I have no absolute max, nor do I have an absolute min. Okay? In the middle, there's a theorem 1. So look at that theorem, read that, see if there are any questions there. We have the extreme value theorem. If f is continuous in a closed interval a and b, then f has both a maximum value and a minimum value in the interval, right? So if you have closed on both sides, just as we saw, there's somewhere you're going to have an absolute max and somewhere you're going to have an absolute min. So if I have a function that looks like this, okay, if I have a function that looks like this, I'm going to have an absolute min here and an absolute max here, okay? All right? And those things are kind of shown there on the bottom of the page, on page 194. You can see that, right? Okay. Then on page 195, now we talk about the local extrema, local max and local min. Okay. So local max and local min, let's look at the green box and the definition there, read that, and see if that makes any sense to you. It says, let C be an interior point of the domain function, then f of C is a local max if and only if f of C is greater than or equal to f of x for all x in some open interval containing C, okay? So let's go ahead and look at that graph up there. Let's go ahead and see if we can talk about that graph. The graph looks like this, okay? So this point here is a local min, okay? It's a local min because what? You have between this interval, this open interval, it is the maximum value, right? Same thing here. If I go from here to here, this point here is going to be a local min because in this open interval here, it is the smallest value. It is the minimum value. It is not the absolute min, right? The absolute min would be down here, right? Okay. Same thing over this is the local max. This here is your absolute max, right? So we can, as we said before, as we talked before prior, right? Any absolute max has to be a local max, right? Any absolute min has to be a local min. Okay, all right. So that's that. And let's go a little further. And we'll talk about finding extreme values. So how do we find these values? What's happening here? What's happening at the local max and local mins? What's happening here? Anybody tell me what's happening here? What's happening with the f prime? What is the value of f prime here? What is the slope?
Down.
Huh?
It's going down.
What is the, if I ask you, what is the tangent, what is the slope of the tangent line at this point? What is it?
0.
0, right? It's going to be 0, correct? So this means that we have an interest when we're trying to find a local max and local min, or actually the extreme max or extreme min. We're always going to try to look for where points where f prime is going to be equal to 0. Okay, that's what we're going to be looking at. So if you go down to page 195 on the bottom, there's theorem 2. Local extreme values. If a function f has a local max value or local min value at an interior point, and if f prime exists, then the f prime of that value, that point is going to be 0. Right? That's what they're saying there. Okay. Further, if you flip the page, we have two different things here. We have what is called a, oops, leave this here. We have what is called a critical point and what is a stationary point. So we have a critical point and a stationary point. Okay, go ahead and read the definitions there. Critical point. Critical point says a point in the interior of a domain of a function where f prime is equal to 0 or f prime does not exist. Okay? A stationary point is the point in the interior of the domain where f prime is equal to 0. Okay? So, therefore, so a critical point is where f prime is equal to 0 or f prime does not exist, right? Where a stationary point is where f prime is equal to 0. So this is a critical point or a stationary point. Anybody?
Both.
Both, right? Because f prime is equal to 0, correct? So it's a critical point and a stationary point. What about the point down here? Is that a critical point or a stationary point?
So both again.
Both again. What about the point up here?
Both again.
Okay, what is f prime at this point?
0. Oh, it's not, does not exist.
Does not exist, right? Because the f prime, as you approach from the negative sign and as you approach from the positive sign is different, correct?
Oh, because it's pointy, not curved.
No, it's a point, right? It's a point. Remember when we had these type of things where the f prime did not exist, okay? So is it a critical point or a stationary point?
Critical?
It's a critical point because f prime does not exist, right? F prime is not 0, it just does not exist, okay? So as you can see, the points of interest for us are going to be the critical points, okay? Where also, one thing that we can say here is that every stationary point is going to be a critical point, correct? Right? Because f prime is going to be equal to 0 at the stationary points. So every stationary point is a critical point. Okay? All right. So let's go ahead and stop right here and start working on some of the homeworks. And then we'll finish up 5.1 after we on the second half. All right?